Hi everyone. So in today's video, I'm going to go over this paper titled LoRaMoE, Alleviating World Knowledge Forgotten in LLMs via MoE-Style plugins. Let me just make sure this is recording. Yeah, this is recording. All right. So the reason I'm going over this paper is because I'm very interested in learning more about how people are merging and mixing LoRa submodules because it seems like a very obvious next step, and this is one of the more recent papers from ACL 2024. All right, so without further ado, let's get right into it. This is my first time reading this paper, and I basically found this by searching for LoRa in the ACL anthology website, and this was like the first paper which showed some kind of mixture of LoRa thing in the title. All right. So SFT is a crucial step for LLMs, enabling them to align with human instruction and enhancing their capabilities and downstream tasks. Yep, ChatGPT is basically just this. Substantially increasing instruction data is a direct solution to align the model with a broader range of downstream tasks, or notably improve its performance on a specific task. However, we find that large-scale increase in instruction data can damage the world knowledge previously stored in LLMs. Okay, this is interesting. To address this challenge, we propose LoRaMoE, a novel framework that introduces several LoRa adapters and integrates them by using a router network, like a plug-in version of MoE. It freezes the backbone model and forces a portion of LoRa's to focus on leveraging world knowledge to solve downstream tasks to alleviate world knowledge forgetting. Okay, and experimental results show that as the instruction data increases, LoRaMoE can significantly improve the ability to process downstream tasks while maintaining the world knowledge. And they have code as well. Okay, I should close all the other tabs. Mhm. I'll give it a star and check it out later, but this seems interesting. Let's see. Introduction. SFT provides a pivotal technique to make LLMs follow human instructions and improve their performance. Although some studies indicate that LLMs trained on a little data can follow instructions well, increasing the amount of data is a straightforward way to enhance the ability to perform multiple downstream tasks. However, the large-scale increase in instruction data can destroy the world knowledge stored in LLMs as illustrated in the right of figure 1. Let's see. First, let's just read what this is. Specifically, as the amount of instruction data increases, we observe a notable decline in performance on closed book question answering, which are used to measure uh, world knowledge in LLMs. In the paradigm of SFT, the conflict between maintaining world knowledge and improving its performance by scaling up instruction data has not been thoroughly examined. Okay, let's see. So left with the number of fine-tuning data, when the number of fine-tuning data increases from 10K to 3 million, the performance of many downstream tasks is significantly improved. So when you have 100K, okay, these are the tasks. I recognize some of them I don't, but at a very high level, it seems that as you're increasing the training samples, your performance increases, which is also what I would think would happen. But what happens with the number of training samples? With the amount of instruction data increasing, fine-tuning the language model results in a decline in performance on benchmarks that measure their world knowledge, such as trivia QA, natural language questions. This is interesting. I thought with fine-tuning this should also increase because now you're eliciting. I just wonder how much of this is the model now being more verbose in its responses and not just the model not knowing it. Okay, and how much of this is just a failure of being able to evaluate it in a good way. When you have like 5 million training samples, you can see the performance is quite worse across benchmarks. Okay. In this paper, we propose LoRaMoE, a novel framework for supervised fine tuning to enhance the model's capability of solving downstream tasks while alleviating world knowledge forgetting. LoRaMoE is a MoE style plugin that introduces several LoRa adapters as experts and integrates them by using a router network. The router network automatically assigns weights to experts, which can improve the LLM's performance on multiple downstream tasks. Okay, so I'm interested in how the router also works. We'll go over the figure when, of course, we reach it in the text. To demonstrate the efficacy of a proposed method, we conduct extensive experiments across a range of downstream tasks. Experimental results show that LoRaMoE can significantly improve LLM ability. to address the various downstream tasks by fine-tuning the model on a large amount of instruction data while maintaining the world knowledge. In addition, we further evaluate our model by visualizing the expert weights for tasks. The result indicate that LoRaMoE adequately alleviates world knowledge forgetting and achieves an improvement of model by fostering collaboration among experts. Okay, I'm also interested in what does collaboration among experts mean. So the main contribution, we find that significantly increasing the amount of instruction data during SFT can damage the world knowledge. The need for improvement in downstream tasks by scaling up instruction data conflicts with maintaining the world knowledge. Okay, they create LoRa MoE, alright, and extensive experiments demonstrate efficacy. Okay, and the visualization experiments show that LoRa MoE fosters collaboration among experts. So let's see motivation. In this section, we verify that a large-scale SFT can cause irreversible damage to world knowledge within the LLMs while improving the LLM's performance in various downstream tasks. So we construct a dataset containing 7 categories of tasks with a total of 5 million samples and use it to conduct SFT on Llama 2 7B. And the implementation is appendix. Okay, I don't care about the hyperparameters. I'm assuming they did hopefully tune it a bit. During the expansion of fine-tuning data, we observed a diverging trend in the performance across two types of tasks as shown in figure 2. Figure 2. Okay. So you can see that hmm, when the data scale increases, some tasks clearly become better, but it also seems to plateau off like 1, 3 million, 5 million, not much far apart. But on other tasks, the performance seems to decrease, which are these world knowledge benchmarks. Okay. So across downstream tasks such as summarization, MT, and others, the performance shows a magnificent increase and eventually stabilize. However, for the other tasks that measure the world knowledge, the performance catastrophically declines. Okay. Notably, with the training data expanding, a contiguous decline can be witnessed. Moreover, this decline will occur earlier if the test set is filtered. Considering previous work that has noted train test overlap, we elaborately select parts of the CBQ dataset without train test overlap for our testing, namely filtered NQ and filtered trivia Q. Okay, nice. So basically, they're also accounting for data leakage and for some things which the model might see during its pre-training, the results might become skewed. So they need to account for that. Irreversible knowledge forgetting. In this section, we dissect the reason behind the decline on these world knowledge benchmarks during the expansion of fine-tuning data. We find this result from the occurrence of irreversible knowledge forgetting inside the LLM. The performance on, okay, irreversible is also a very strong claim. This means that you can't really recover it via any other fine-tuning method. This seems like a strong claim. The performance on world knowledge benchmarks highly relies on the knowledge and skills learned during pre-training to investigate the relationship between the performance on world knowledge and knowledge embedded in pre-trained models. We conduct fine-tuning solely on the CBQA dataset with 250K samples and run evaluation on the test set without overlap. Results in figure 3 show initial training boost performance significantly, especially the first 1% with limited gains thereafter. This is because early fine-tuning aligns existing knowledge with new instructions. However, due to minimal train test overlap, adding more samples doesn't further enhance this model's benchmark success relies on world knowledge acquired from the pre-training. Okay, this is interesting. The performance on world knowledge benchmarks after training on CBQ is solely, and this is with the number of samples. So you can see that, okay, the sale is 1E5 is, I guess, 100,000, if I'm not wrong. 100 is 1E2, 1E3 is 1,000, 1E4 is 10,000. Yeah. So when you have like close to 100,000 samples, the performance increase is not super high when going from say 100,000 to 250K, while just 1%, which seems to be this portion, you can see quite steady gains. Okay, given that it is naturally assumed that the diminishing performance or knowledge benchmark stems from the damage of knowledge stored in LLMs due to large-scale instruction tuning, to verify the hypothesis, we sequentially fine-tuned the model using two datasets. First, excluding CBQA dataset, and then with the CBQA, results presented in table 1 show a great decline. Uh, in knowledge capture capabilities versus the original LM. This indicates that the world knowledge within the model was compromised during the first stage, resulting in the model's inability to force alignment between human instructions and the already destroyed knowledge solely with CBQA. This is table one. Okay. So your baseline score on Trivia QA is 33.5. If you do SFT on CBQA, you get 36.2. But if you do this two-stage fine-tuning, uh, where the first stage is model tuned on 3 million instructions, it's much worse. Similarly for NQN, hotpot QA as well. Okay, the numbers seem to be pretty clear about this. Let's see what they do. In this, to sum up, the pursuit of enhancing performance on downstream tasks through the expansion of training data conflicts with the preservation of world knowledge within a model in vanilla SFT. In this section, we elaborate on the methodological details of LoRaMoE, which is an MoE-style plugin, and introduce localized balancing constraint during the training phase to alleviate the world knowledge as shown in figure 4. Okay, so if you look at classic MoE, you have the transformer block, but inside the transformer block, you have multiple feed-forward networks with a router. Then in LoRa MoE, you essentially have multiple LoRa's per feed-forward network, and only these LoRa's and the router is being trained. Okay, now the architecture. Uh, in MoE, the router assigns weights of experts according to the data, allowing them to divide the labor to complete the forward process. The key side of LoRa MoE is that we freeze the backbone model and introduce experts to leverage this knowledge while improving the performance on multiple downstream tasks. Additionally, we utilize the LoRa as the architecture of the expert to improve training and inference efficiency. So formally, for the traditional transformer, the feed-forward network is just this. So you apply feed-forward on the input, and also this residual connection. And you can also think of this as this matrix operation, which is basically you have W times X, where W is composed of W naught and this delta W term. Uh, so delta W is basically your LoRa weight. For LoRa MoE, we replace the linear layer with the MoE-style plugin, which makes experts collaborate. During the training phase, we freeze the backbone. Consider the LoRa MoE containing n experts, so which is denoted by all these EI 1 to n. The forward process can be written as basically you have some uh, EI, which is the uh, particular LoRa expert, and then you also get this weight, which is coming from G, and you basically aggregate this across all the LoRa experts and then add this to the base model. So G is basically softmax of the input times the weight matrix WG. Let's see what is WG. WG is the trainable parameter matrix of the router network. So this basically tells you based on this input how much weight should I give to different mix experts. By this, the experts and the outer world in tandem enabling the experts to develop varied capabilities and efficiently handle diverse types of tasks. In addition, LoRa has been proven to be both effective for SFT to enhance the efficiency and resource conservation of the fine-tuning process. We replace the parameter matrix of the experts with a low-rank format. Specifically, the matrix delta WE of the expert E can be expressed as B times A, which is basically what your LoRa is. LoRa contributes to significantly reducing the trainable parameters. Overall, since so at this point, EI was just a feed-forward network, but now you've also basically explicitly written out what EI is. EI is basically you first multiply by this matrix AI for, and then by the outward projection of that particular LoRa export, which is BI. You also scale by alpha by R, which is how these LoRa models work. This is like the hyperparameter which weights the LoRa contribution. And Wi comes from the route. Alpha is a constant hyperparameter, approximately equivalent to the learning rate. Okay, I haven't seen this written out, or have I? I don't remember. Maybe I'll need to check the original LoRa paper. I do remember that alpha. There was some comparison for alpha. Alpha was usually close to the rank value, if I'm not wrong, but yeah, approximately equivalent to a learning rate just seems a bit off for some reason. Localized balancing constraint. The imbalance of expert utilization is a typical problem in MoE. It is also observed in this solution. The conventional solution is balancing expert utilization, which involves making the coefficient of expert's importance as the law function, variation, which involves making the coefficient of variation of the expert's importance as the loss function. However, this method assumes all the training samples are under the same distribution, which ignores the fact that samples may be coming from different distribution, for instance, QA and other downstream tasks. So considering the mixed characteristic, during the training phase, we introduce localized balancing constraint, a novel balancing expert utilization method to make portion of experts focus more on leveraging world knowledge to solve tasks. As shown in figure 6, during the fine-tuning phase, we softly constrain experts to concentrate on two aspects, one of which focus on leveraging world knowledge, while another focuses on other downstream tasks. In addition, all experts within the same aspects are balanced, such as balancing expert utilization. Okay, so within one aspect, you're all experts in the same aspects are balanced. So all experts for one kind of tasks are balanced, like world knowledge. Let's see. So you have balancing within a group, and then you have localized balancing constraint. So you softly force experts to focus on two types of tasks. Formally, we define the importance matrix Q of the LoRaMoE layer, and Qn, M denotes the sum of router values of the nth expert for the emit training sample in the batch. So let me read this. We define the importance matrix Q of the LoRaMoE layer, and Qn, M denotes the sum of router values of the nth expert for the emit training sample, which can be represented as follows. So you basically take N and TM are the number of experts. So basically summing over the number of no, TM is the number of tokens of the emit training sample. So you're summing over all tokens and you're computing this GXJI. G was your, I believe, your router thing. Yeah, your routing thing. And then you're basically summing over all the experts and getting this normalization. So let's see. XJ is the hidden input of the J8 token. So taking the J8 token's hidden input and seeing the weights for the different experts. We define the coefficient matrix I with the same size as Q corresponding to the importance matrix Q. I n comma m denotes the importance coefficient of Q n comma m. So if it has the same type, it increases by delta, and if it has a different type, it slightly decreases by delta. And well, delta belongs to 0 to 1. Type en, and this basically predefined target types of nth expert and the task type of the emit training sample in a batch. So if the type of the nth expert is same as the task type of the emit training sample, you basically increase the importance. We categorize the instruction data into two distinct types, world knowledge and other downstream tasks related. Then we enable a portion of expert to learn on this one and some to learn on the other. Formally, suppose I comma k and I j comma k denote the importance coefficient of the ith and jth expert for the kth sample respectively. If experts are in the same group, their values at corresponding positions are identical. So both world knowledge experts will have the same uh, importance coefficient. This indicates that these experts have the same importance because they are assigned to focus on learning the same task. On the contrary, values of experts for different groups would have different coefficient. Now, the localized balancing constraint is defined to measure the dispersion of the weighted importance matrix, which is I dot Q, which can be mathematically represented as you're basically taking the variance and the mean, and variance by mean is the loss. Specifically, if a specific sample is from world knowledge related dataset Experts focusing on solving this type will have larger values in the coefficient matrix I. Yes, optimizing this loss, the loss reducing can make corresponding experts learn more from the sample and be assigned a larger weight by the router. Meanwhile, experts solve the same type of tasks are balanced. In addition, the constraint is soft to encourage cooperation among experts. Okay, so yeah, I think so far this makes sense. This part is a bit tricky for me to understand at the moment. Maybe it will become more clear as we read the paper. It just seems like they're doing an element wise scaling here. So each thing, each coefficient, each weight of that thing, importance of that thing is multiplied by that corresponding position in Q. So if a specific sample is from world knowledge related dataset, experts focusing on solving this type will have larger values in the coefficient matrix I, and optimizing the loss reducing can make corresponding experts learn more because you want to minimize the variance over the mean. Okay. Overall, localized balancing constraint achieves a localized balance between two types of experts. And yeah, your total loss also now needs to account for this. Beta controls the strength. In the training phase, we freeze the backbone, and uh, I guess they also need to tune beta. In inference, the router automatically assigns weights. All right, so okay, they've initialized everything. The hyperparameters for beta and the degree of imbalance are both set to zero point 0.1. For LoRa setting, alpha and R are set to 32 and 4 for the main result respectively. The dropout is 0.05, learning rate this, training dataset is 3 million. Okay. So main result table 2 displays the performance of LoRaMoE and compares this result with the outcomes of directly comparing SFT to the model or utilizing LoRa tuning. The results show that language model with LoRaMoE gets good performance on both world knowledge benchmarks and other, uh, indicating its effectiveness in avoiding knowledge forgetting. For world knowledge benchmarks, contrary to catastrophic forgetting, there's no such issue, but also surpasses the model fine-tuned solely with CBQA. LoRaMoE shows a significant improvement with a up to 63.9% improvement and an average of 35.3% jump. Okay, this is quite good. For other downstream tasks, LoRaMoE is capable of achieving performance close to or even surpassing SFT. Let's look at this. So your baseline was 65.4. If you just do SFT, you get 76. And if you just do LoRa, you stay at 65.4. Okay. LoRaMoE reaches 71.2. It's also much less expensive, to be fair. And with this additional loss, it reaches 70.2. But I guess the main trend is for each row, the bold number is the highest. And this last column seems to have the most highest count of bold numbers. For other downstream tasks, LoRaMoE is capable of achieving performance close to or even surpassing direct SFT. For instance, in all reading comprehension, LoRaMoE achieves superior performance. They also compare against PEFT by a single LoRa. The knowledge forgetting also occurred during single LoRa fine-tuning as it is essentially the same as vanilla SFT. Hmm. Compared with a single LoRa, multiple collaborative LoRas enhance both world knowledge. I don't really agree with this because it does not have as many parameters to overfit to the new data. And in some of our own works, which you'll see on archive soon, we've also noticed that LoRa fine-tuning preserves performance on benchmarks as well. Let's see. Now, this is the average numbers. This additional loss improves outcome for a vast majority of tasks, both world knowledge and others. Okay, up to a 17.6% improvement, which is quite good. Now, for sensitivity analysis, keeping other constraints same, we vary number of experts and the rank of LoRa. And I guess the results are in table 3. As the number of trainable parameter increases, performance is generally stable. So more the rank is more perform. Okay, if you have rank 16, it's not too far off in terms of average results. And number of 6 experts is the most beneficial choice according to them, as more experts do not lead to higher performance. So okay, 8 is not it is in fact worse. Okay, and less is also worse. They seem to have hit the sweet spot. And then if you try to visualize the expert utilization, this is present in figure 7. So for instance, for type 2, experts are more active in type 2 tasks, and type 1 experts are more active in type 1 tasks, which is as you would expect since you're doing this soft constraint. There's a distinct contrast in utilization. Yes, this suggests that routers can automatically allocate specific tasks to experts with corresponding abilities during their inference phase. Specifically, the experts are requested to leverage world knowledge are greatly employed in world knowledge questions, underscoring their vital role in preventing this forgetting. This corresponds to the fact we state in section 2 that supervised fine-tuning boosts the model's capabilities in these tasks by associating pre-stored world knowledge in the model with human instructions. On the other hand, experts assigned to focus on enhancing performance are given increased prominence when encountering these tasks. And yeah, for example, in reading comprehension tasks, knowledge learned during pre-training can better assist to make factual judgments. This phenomenon is even more pronounced in language-based tasks. The router allocates on average about 45% to experts responsible for world knowledge. Okay, so some downstream tasks still require export further types, and this is the justification for it. In terms of related work, we know PEFT, LoRa, LoRa's exist, adapters exist, prompt learning, prompt tuning, p-tuning, everything exists. Yeah, I don't need to know more about that. For MoE, you have this sparsely activated experts. Currently, the token level MoE architectures are widely used. Mixtral very popular. In addition, researchers aim to investigate the router selection problem. Unlike these efforts to expand the model size and address the selection problem, we propose an MoE style framework for multitask learning. Okay, and what already exists for multi-LoRa architectures? LoRa Hub exists to choose different LoRa combinations. MoE LoRa leverages LoRa and MoE for task-specific tuning, especially in healthcare. However, these methods need a data type as the input during the inference phase, which limits the applicability. Okay, I guess they're doing selection of the adapter based on the input the user gives. Shen et al. First introduced multiple LoRa serving system. You also have S-LoRa, which can serve thousands of LoRa's. Shen et al. 2023b introduces several experts to enhance the model's ability for multimodal learning. Unlike these approaches, LoRaMoE introduces a MoE-style plugin and localized balancing constraint to tackle world knowledge forgetting while enhancing the model's ability to multitask. Okay. In conclusion, this is better, of course. For limitations, they limit to 7B due to resource and time. Fair enough. But I would have liked if they did at least the same experiments on more models at a 7B scale. However, we haven't studied the case when there are more expert types. Okay, what if there are 10 types of tasks? Details about experimental setup, the data set, the word knowledge of LLM further decline after being trained with more data. So they're mentioning all the data sets they use. How do you do the expert balancing? So, okay, so this is the derivation, I believe. Let's go over this because the rest is quite simple. They've just uh, written down all the results. But I'm, yeah, a bit interested in Appendix C. So when fine-tuning MoE without any constraints, the router mechanism often converges to a state in which a small number of experts receive a disproportionately large preference. Okay, as exhibited in Figure 5. Figure 5, the coefficient of variation for the experts of the unconstrained LoRaMoE progressively escalates and sustains at a high value, approximately 3, similar to phenomenon observed in the Shazir paper. This indicates that router assigns large weights to the same few experts. Okay, so basically you have, oh, so this now explains why you're looking at the variance here because you want this to be minimized. You want the variance of these uh, variance of importance to be less so that everything gets a fair share or every expert gets hopefully balanced out uh, share of input and It's not like during training everything collapses into one. This imbalance among experts presents a challenge, as experts that receive greater routing weights in the early stages have more optimization. A conventional solution for balancing experts utilization involves employing the coefficient of variation of the expert's importance as a loss function. I guess this is also from the Shazir paper. The solution assumes that the distribution of MOE training samples is a single distribution, which inherently eliminates the necessity of considering the diverse origin. Specifically, this traditional approach simplifies the modeling process by assuming homogeneity in data sources that often do not align with fine-tuning data, where you have both factual Q and other downstream tasks. Therefore, such simplification can lead to significant biases. Okay, traditional balancing constraint, which aims to allocate a uniform distribution of training samples across all experts, can lead to inaccurate parameter estimation. This is because such constraints do not account for intrinsic. Okay, they've written the same thing twice. Recognizing the disparate nature of data distribution, LoRAMoE strategically assigns data to experts not uniformly but based on observed imbalances. This allocation is governed by a set of weights that are calibrated to reflect the varying significance of different data categories. Okay, this is why they're not imposing the constraint on Q, but they're importing the constraint on Z, which is I times Q, which is basically Q balanced by the task type. So for yeah, I think you get the point. Such a specialized allocation method is pivotal in addressing the challenges posed by uneven data distribution. By tailoring the distribution of training samples to each expert based on the inherent disparities in the data, LoRaMoE facilitates a more accurate and representative parameter estimation. This nuanced approach to data distribution allows for a more effective fitting of the model to diverse data subsets, significantly enhancing the model's predictive accuracy and generalization capability. This strategy is particularly effective in scenarios where data imbalance could otherwise lead to skewed learning and generalization errors. To illustrate the concept with a simplified model, let's assume our training data is sampled from a mixture of two Gaussian distributions. So you have mean variance. The proportion of training data from each is P1 and P2. And okay, this is should be lowercase. Sum should be one because of course you only have two subsets. And without loss of generality, you can assume that one subset is less than or equal to the other. So when a MOE model fits the proposed distribution with balance weights M, the likelihood of the model given the data can be estimated as, so you have M times uh, the weights are basically M and 1 minus M, so you have M times this and 1 minus M times this plus M times, wait a minute, am I misreading something? Where card x1 is to card x2 is p1 is to p2 using n1x and n1 n2x for n this and this. The optimal value are by taking the derivative. Wait a minute. So you have m times n. This is the first distribution, mu1 and sigma 1. And then 1 minus m times the second distribution times m times the first distribution. Okay, now, but your x1 and x2 are different. Card x1 is to card x2 is this. Okay, the optimal mean for mu1 dash satisfies the following constraint whose value is 0 when the fitted distribution is in the same value of mixed distribution. So you're basically taking a derivative with respect to mu1 dash. You get this because in any term which does not have mu1 dash becomes 0. And if you expand this out, in equation 10, we can replace part of the summation with the empirical estimate of the mean of input x. For an ideal routing network, there must exist a distribution n such that the data allocated to this distribution is independently and identically distributed. Let's assume the distribution to be n2. In this case, if m is greater than or equal to p1, then the fitted result for distribution will be this based on the chain rule. This is less than or equal to 0. The inverse result can be derived similarly. Therefore, the best training error is achieved only when the mixing coefficient m of the prior distribution is consistent with the actual sampling distribution p1. I did not understand this, but I don't think I'll also understand this very well at the moment because I think this is very poorly written. Or maybe I'm just dumb. I should not say this. I just feel like lot of notation they're using here is not well defined at all. But yeah, what I do realize now is that this entire thing is one term, and this entire thing is one term. So you basically have two products over this proportionate proportion based sum of the two distributions. In one of them, you are taking the product over x1, and on the other of two, you're taking this over x2. But what are x1 and x2 is not clearly defined. And what is card, I believe, is this cardinality or something? I don't really get that. Hmm. Okay. Yeah, anyways, I'll maybe look at this later. Otherwise, the paper is really interesting. I think the main two takeaways from me for me are this figure and then this table, which seems to imply that a mixture of expert style LoRa plugin is quite good. All right. So thank you guys for tuning in. See you around next time.